Hi friends, welcome back. In the previous session, we have completed up to Z-Transform with the realization of the systems also. Now, the next topic what we have to discuss is DTFT, which is called as discrete time Fourier transform. Discrete time Fourier transform, which is similar to that of Fourier transform in the continuous time case. So here we have to use the discrete time signal. So before going for DTFT, I want to see some pairs. What do you mean by that pairs means? In time domain, we are going to get the classification of signal. That means they will give you some characteristics of the signal, and we have to find what is the characteristics of the signal in the frequency domain. Suppose if the signal is a aperiodic continuous time signal, then in the frequency domain, the spectrum how it is going to look like. So these kind of things we have to. So for that, first we have to see some of the things. Let's say what we know. We know some of the things like this. Let's say this is a periodic signal and a continuous time signal. So the signal what we are discussing here is a continuous time periodic signal. Continuous time periodic. Then how the spectrum looks like? Actually, for a continuous time periodic signal, we have to talk about the spectrum of Cn. That means Fourier series spectrum. So if I take Fourier series for this Fourier series, then what we are going to get here is n omega naught. So we are going to get this kind of Cn spectrum you are going to. So this is the time domain, this is the frequency domain. So this is Cn. So if I say what is the nature of Cn? So definitely it is a discrete. So it is, let's call it is a 0. This is a omega naught, 2 omega naught, 3 omega naught, 4 omega naught, like that it is going. So it is a discrete time spectrum as well as it is aperiodic in nature. So it is discrete aperiodic. Discrete and aperiodic. Now let's take one more thing. Suppose if I take a signal which is like rectangular pulse, x of, then what is the nature of x of t actually? This is continuous time aperiodic, continuous time, and we will write continuous and aperiodic. Aperiodic. Here also continuous and periodic. Continuous and periodic. So if I try to find out Fourier transform for this, Fourier transform, what kind of signal we are going to get? We are going to get sampling function x of omega. This kind of signal we are going to get sampling. Okay. So what is the nature of this spectrum? The nature of the spectrum is continuous and aperiodic. Continuous and aperiodic. Let's take two TS, three TS, minus TS, minus 2T. So it is called as sampled signal, XS of t, sampled signal. So in the sampling, what we are going to get is a discrete time signal, and it is aperiodic. So what we are getting is a discrete aperiodic. Discrete and aperiodic. If I try to find out the Fourier transform for this, how it is going to look? Fourier transform. So I have given you a generalized thing which looks like, let's call it is a oversampling. Let's call it is a oversampling. So this is what we are going to get: 0, omega s, minus omega s, shifting. We have seen in the sampling theorem, oversampling case, if I take. So what is the nature of the spectrum here? This is continuous and periodic. Continuous and periodic. So with this, we are having some conclusion points what we can make. So let's try to understand. If you write continuous, continuous, with this we can say aperiodic, aperiodic. Here is continuous, aperiodic. Periodic, discrete, discrete, periodic. So I can say there are pairs. What are the pairs actually? So pairs, we can say continuous. Whenever you see continuous, for this the pair is aperiodic. Aperiodic. Whenever you see discrete, you can say periodic. You can say periodic. So these are the pairs. So what do you mean by that? That means in time domain, if the signal is continuous, in the frequency domain, it is aperiodic. In the time domain, if the signal is discrete, in the frequency domain, it is periodic. In the same way, in the frequency domain, if it is continuous, in the time domain, it is aperiodic. In the frequency domain, if it is discrete, then in the time domain, it is periodic. These are the pairs. So in one domain, if you see continuous, in other domain, you can see aperiodic. In one domain, if you see periodic, then in other domain, you can see discrete. Definitely. Let's see. So let's see whether it is matching or not. Continuous, whenever it is continuous, there we have to see aperiodic. Yes. Here it is periodic. For this pair is nothing but discrete. Yes, discrete is there. Next, continuous. So continuous, sorry, aperiodic. Aperiodic, continuous. Discrete, periodic. Aperiodic, continuous. So these are the pairs you have to remember. Okay, take it. Please take it. So these kind of questions will ask in the IES examination sometimes. They will give you the nature of the signal in the time domain. They want to find out what is the nature of the spectrum in the frequency. Or they will give you the spectrum nature. They want to find out the nature of the waveform that is in the time domain. Clear? Take it. I can enter into DTFT now. Let's see. In the DTFT, so it is similar to that of Fourier transform for continuous time signal. So there in the continuous time signal we have used continuous aperiodic signal. So here we are going to use discrete time aperiodic signal. So for a discrete time aperiodic signal, what is the frequency content we are having? So to find out that, we have to use the DTFT, discrete time Fourier transform. So here, let's say x of n is given to you for this DTFT, discrete time Fourier transform. They can represent it in so many ways. Let's say x of e power j omega. I told you that can be replaced with e power j omega, or x of e power j omega, this kind of notation also, or x of omega or j omega. But in the examination, they will give you this kind of notation. So please, in so many textbooks, so many notations are there, but I will follow this notation, x of e power j omega. That means x of z is there. If z is replaced with e power j omega, we are going to get x of e power j omega. So here, x of n, x of e power j omega. So let's see. Here, what is the nature of x of n? It is a discrete time signal and aperiodic signal. So it is discrete and aperiodic. This is going to give you x of e power j omega. What is the nature of that x of e power j omega? Just now we have seen some pair. In that pair, discrete is going to give you periodic nature and aperiodic is going to give you continuous nature of the spectrum. So here we are going to get a continuous, it is a continuous spectrum and periodic spectrum. Periodic. This is very, very important. So DTFT of any discrete time aperiodic signal is going to be a continuous spectrum and it is a periodic. And I am just giving you without any proof, it is having period is equal to 2 pi. Period is equal to 2 pi. And what is the central frequency? Minus pi to pi. Central frequency. Minus pi to pi. So this is nothing but the period we are going to consider. What do you mean by this? You can understand. Let's say. So if x of n is given to you, it is actually capital X of e power j omega. X of n is given to you, then how can you calculate x of e power j omega? In the Z transform, we have seen somewhat introduction for this DTFT. So this is summation n is equal to minus infinity to infinity x of n e power minus j omega n. J omega n. So this is what we are going to do. Now there is a reverse formula also. If you know DTFT, how we can calculate inverse DTFT? That is nothing but x of n. Then 1 by 2 pi integral minus pi to pi. It is not minus infinity to infinity because it is a periodic signal. And we are using integration. Why we are not using summation? Because in the frequency domain, it is a continuous function. So we have to use the integration. X of e power j omega e power j omega n d omega. So this is the formulas what we have to remember for a discrete aperiodic signal DTFT. We are having that. Yes. Now coming to this one, x of e power j omega. Just now I told you it is a periodic with a period 2 pi. So whether it is a periodic with a period 2 pi or not, that's what I want to check. Let's see. X of n, if you know, then what is x of e power j omega? Is summation n is equal to minus infinity to infinity x of n e power minus j omega n, where n is an integer. Now x of e power j, I told you it is a periodic with period 2 pi. That means if I replace omega with omega plus 2 pi or omega with omega minus 2 pi, it has to be the same because it is a periodic with period 2 pi. So omega plus 2 pi I am taking. Let's check it out whether it is going to give you the correct answer or not. Means same x of e power j omega or not. Summation. Wherever omega is there, replace it with omega plus 2 e power minus j omega plus 2 pi into. So this can be written as summation n is equal to minus infinity to infinity x of n e power minus j omega n multiplied with e power minus j 2 pi n. What is e power minus j 2 pi n? Which is equal to cos 2 pi n minus j sin 2 pi n. J sin 2 pi n value is equal to 0 and this value is equal to 1. 1 minus j 0, that is equal to 1. So finally I can replace it with 1. So finally what we got? Summation n is equal to minus infinity to infinity x of n e power minus j omega n. Then this is nothing but the x of e power j omega, x of e power j omega. So I hope you understood. X of e power j omega plus 2 pi. So you can write plus or minus, plus or minus, plus or minus means minus or plus, minus or plus. So still it is 1. I hope you understood. So that is nothing but x of e power j omega is periodic with period 2 pi. So that is x of e power j omega is periodic with period 2 pi. This is what we have discussed. Clear? So I hope you understood. Take it. Formula is similar to that of Fourier transform only, but only it is a summation, not the integration. Yes, domain. Z domain. In the S domain, the reference axis is j omega axis. That is nothing but the frequency axis. J omega axis is the frequency axis. Now, if I take this vertical line, okay, so from here to here, in this direction, if I go, so here omega is equal to minus infinity to 0. So if I go from here to here, omega is equal to 0 to omega is equal to infinity. So I can say what is the range of omega? Range of omega, which is minus infinity to plus infinity, minus infinity to plus infinity. So here, what is the testing range? Suppose if I want to test any system, then we have to consider only positive frequencies. Testing range of omega. That means 0 to infinity. Testing range is from 0 to infinity. Now if I write testing range of S, testing range of S, that is also 0 to infinity. If omega is equal to 0, S is equal to 0, omega is equal to infinity, S is equal to infinity. Okay. So this is what we are going to get, testing range. Now try to understand. In Z domain, it is similar to that of unit circle. This is real axis, imaginary axis. So we are having a unit circle. Unit circle. Okay. In that unit circle, the angle here is nothing but omega. So here it is not an angle, it is a value which is changing from minus infinity to plus infinity. Because in the Z domain, it is an angle, so it is having some limitations. What is that? See, while we are mapping from S domain to Z domain, the line, this vertical line, which is changing from minus infinity to 0, is actually this lower circle. This lower circle. This lower circle. So if it is a lower circle, so its value is changing from, so what is the omega value here? It is minus pi. It is 0 here. Next, here this upper straight line, vertical line, which is similar to that of this upper circle, half circle. So here omega value 0, angle is 0 and angle value is equal to pi. So if I ask, what is the range of omega here? Range of omega, which is minus pi to pi, minus pi to pi. Now, what is the testing range of omega? Which is 0 to pi. We don't take negative frequencies. 0 to pi. If I ask, what is testing range of Z? What is this testing range? You can understand later. Testing range of Z. So let's say at 0, what is the Z value? So at this point, what is the Z value? At 0, Z is equal to 1. At omega is equal to pi, what is Z is equal to? Minus 1. So this is very, very important. 1 to minus 1. So here testing range means, suppose if I want to test a signal or system, I can call this omega is equal to 0 as a low frequency, omega is equal to infinity as a high frequency, or in S also we can say low frequency, high frequency. But in the Z domain, or we can say in the discrete time case, the low frequency is 0. High frequency is not infinity, actually it is pi. Why? Because after pi it is keep on repeating, minus pi to pi, the same thing is going to keep on repeating. So I can say 0 to pi, this is lower frequency, this is higher frequency. But in the Z, the lower frequency is equal to 1, a higher frequency, that is infinite frequency, is similar to that of minus 1. Be careful. So many people think that 1 is a high frequency, minus 1 is a low frequency, but that is not the case. 1 is the low frequency, minus 1 is the high frequency. Is that clear? Take it. So let's see symmetry property of the DTFT. This is well-known property. Whatever the Fourier transform we are having, the same property will be continued. Symmetry property. Symmetry property. What is the symmetry property? Let's say, first if I say x of e power j omega is summation n is equal to minus infinity to infinity x of n e power minus j omega. If I expand this e power minus j omega n, that is nothing but cos omega n minus j sin omega n. So if I expand it, this summation will be two parts. Summation n is equal to minus infinity to infinity x of n cos omega n minus j summation n is equal to minus infinity to infinity x of n sin n. So once we calculate this value, so it is entirely in terms of omega. So we can call this as a of omega minus j b of omega. So if you observe carefully, a of omega, real part of x of e power j omega, is nothing but a of omega. So here a of omega, if I take a of minus omega, is it going to give you the same answer? That means real part is nothing but an even function of omega. A of minus omega is equal to a of omega. So from this we can say real part is nothing but even function. In the similar manner, we can say what is b of minus omega? So that will become minus b of omega. So I can say imaginary part of x of e power j omega is going to be odd function. So from this I can say x of e power j omega in general is a complex spectrum. That means it is having real part as well as imaginary part. So in this, real part is a even function and imaginary part is a odd function. So in general, this will exhibit conjugate symmetry or even conjugate. So I can say x of e power j omega exhibit conjugate symmetry. Conjugate symmetry. So because it is exhibiting conjugate symmetry, we are having a table which is we know x of n x of e power j omega. So this table will never fail. What is that? If in time domain signal is real and even, then in the frequency domain it is a real and even. If it is real and odd, then it is imaginary and odd. Imaginary even is imaginary even. Imaginary odd, real odd. So if it is a real and neither even nor odd, then we are having complex and conjugate symmetry that exhibits conjugate symmetry. Clear? Take it. These things we already know. That's why I haven't proved anything. I'm directly giving you. Whenever a signal is satisfying conjugate symmetry, they will give you this kind of result. And here also we can say spectrum, that is a spectrum. We are having two spectrum. One is magnitude spectrum. Magnitude spectrum means mod x of e power j omega versus omega. So this is going to be even function. Next, second one, phase spectrum. That is angle of x of omega, x of e power j omega versus omega. This will exhibit odd function. Odd. Z-Transform of x of n is same as DTFT of x of n r power minus. This is the thing what we have seen. At r is equal to 1, r is equal to 1. It implies what is z is equal to e power j omega. E power j omega. We are going to get Z-Transform and DTFT are equal. DTFT are equal. So what I am trying to say is, we can calculate DTFT from the Z-Transform by replacing Z with e power j omega. I can calculate DTFT from Z-Transform by replacing z with e power j omega. That's okay. But is it possible to replace z with e power j omega in every signal? No, we cannot do that. So it is possible only for energy signals and bounded signals. For unbounded signals, DTFT does not exist, similar to that of Fourier transform. Because in the Fourier transform also we have seen, for unbounded signals we will never write the Fourier transform. Only for bounded signals we are having the Fourier transform. Here. So I am writing that point here. We can calculate, we can get DTFT from Z-transform, from Z-transform by replacing Z is equal to e power j omega t, j omega e power j omega. Replacing Z is equal to e power j omega, but x of n must be energy signal. Energy signal. For energy signals only it is a possibility. Okay. Energy. Next thing is we can say for unbounded signals, DTFT does not exist. Does not exist. So these are the very important 2 points you have to remember. Okay. So let's see some of the things what we can do. Suppose x of n is given to you delta n. What is x of e power j omega? That is simply 1. Without much thinking we can say x of e power j omega is equal to summation n is equal to minus infinity to infinity delta n e power minus j omega. So n is replaced with 0. This is going to be summation n is equal to minus infinity to infinity delta n we are going to get, which is equal to 1. So in short, remember for delta n, DTFT is equal to 1. Next, suppose if the signal is given like this, x of n is equal to a power n u of n, and here mod a less than 1. Why this condition has to be mentioned, mod a less than 1? Because if mod a greater than 1, this will become growing exponential. If it is a growing exponential, it is an unbounded signal. If it is an unbounded signal, we cannot find DTFT. DTFT does not exist. Is that clear? So for bounded signals only DTFT exists. So the condition must be mod a less than 1. That means decaying exponential has to be there. Why? It is a bounded signal. So for bounded signals only we can. Now for this we don't go for a formula. Actually what we know, because it is a bounded signal and it is a energy signal, we can directly go from Z transform to DTFT. How, sir? For this signal we know Z transform, right? What is x of z? That is 1 by 1 minus a z inverse. This is what the Z transform, right? So in this Z transform, if z is replaced with e power j omega, then what we are going to get? 1 by 1 minus a e power minus j omega. So this is what the x of e power j omega, DTFT, directly we can say. Is that clear? Check it. So we can directly calculate DTFT by simply replacing z with e power j omega, because it is a energy signal. Decaying exponential. Find inverse DTFT of x of e power j omega is equal to summation m is equal to minus infinity to infinity delta omega minus 2 pi m 2 pi. For this signal, we have to calculate x of n. Okay, I just want to say this. You might remember for delta t in the Fourier transform I am talking about. So in the Fourier transform continuous time case, delta t having Fourier transform 1, and for 1 we are having 2 pi delta omega, or we can say for 1 by 2 pi we are having delta omega delta. So here also the same thing we can say. This is also similar to that of delta omega only. That means delta omega. If I draw this function, how it is going to look like? Let's see, with respect to omega. M is equal to 0. That means delta omega at 0 we are having 1. Next, if m is equal to 1, delta omega minus 2 pi. If m is equal to 2, 4 pi. Minus 2 minus 4 pi. So actually I am trying to say it is similar to that of delta omega only. How, sir? How it is going to be similar to delta omega? Delta omega means it is existing only at 0, but it is existing at 2 pi, 4 pi. Yes, because DTFT is a periodic nature. To preserve that periodic nature, we have to show delta omega at 2 pi. This is the impulse function at 4 pi, 6 pi, 8 pi, like that. So it is a repetition after 2 pi radians. Why? Because it is a periodic signal with period is equal to 2 pi. So it is exactly same as delta omega. Let's say if you got doubt, so I will calculate x of n here. What is x of n? 1 by 2 pi integral minus pi to pi x of e power j omega e power j omega n d omega. Clear? See here. I am taking minus pi to pi, minus pi plus. So this is equal to 1 by 2 pi minus pi to pi. Minus pi to pi, we are having only one impulse function, that is nothing but delta omega e power j omega n d omega. So any function multiplied with delta omega, omega has to be replaced with 0. This value will become 1. If this value will become 1, this is nothing but 1 by 2 pi integral minus pi to pi delta omega d omega. So if you observe carefully, what it is going to give you, this is value is equal to 1. Finally, we are going to get 1 by 2 pi. 1 by 2. So I hope you understood. In the time domain, 1 by 2 pi is going to give you in the frequency domain this kind of periodic signal, which is nothing but delta omega. So I hope you understood why it is a periodic, why it is 1 by. It is exactly same as this one only. This is similar to this one only, delta omega having 1 by 2 pi. But here it is a periodic signal. That's why we have to show delta omega minus 2 pi. Okay, I hope you understood. Take it.